Okay, we're going to work on simplifying radicals. And so the handout that was available online is basically like flashcards. So just to kind of preview that, the first page has 6 problems on it that the directions are all to simplify the radicals. And then the second page is the answers to that. So you can see that if this was question 1, if you were going to flip the page over, then this would be the answer to 1, and then this is 2. This is the answer to 2. So if you print it out double-sided, you kind of have some flashcards. So we're going to work on simplifying some of these together just to get you an idea of how this all works out. And so let me erase that back up, and we're going to open up just that first page. So when we're talking about simplifying radicals, we're looking at radicals that are no longer perfect squares or perfect cubes. So a little reminder, just in case you have forgotten, we have perfect squares. So like the square root of 1 is a perfect square because 1 times 1 equals 1. The square root of 4 is 2. The square root of 9, 3, and we could keep on going. Square root of 25, which we've listed these before, like when we were factoring with difference of squares. And it goes on and on. And so we want to be familiar with how to simplify those, but those are perfect squares. We also have the perfect cubes, which are written with that little index of 3. And we could say like cube root of 1 is 1, the cube root of 8 is 2, cube root of 27 is 3, and we can keep going. Now, 2 things that you need to keep in mind is that when you're taking a square root, you need a number times itself. That will get you that number. So if I'm asking you to find something like the square root of negative 25, there's no real number that can get you that. Like you might think like, oh, well, I think the answer is negative 5. So that would mean that negative 5 times negative 5 will equal, but wait, it's not negative. It becomes a positive 25. So negative 5 can't work, and we know 5 doesn't work. So that's when there's going to be a whole nother number system, which we'll talk about soon, which is the imaginary numbers. So for now, we just say that there's no real number for that. And again, it's because we have, even though you don't see it, it's an even index. So we want something that multiplies an even number of times. That's different than our perfect cubes when we have that odd index. So if I ask you to find like the cube root of negative 8, that one actually does have an answer. It's negative 2. And that's because an odd number of times gets us negative. So what I mean is like negative 2 times negative 2 times negative 2. That will equal a negative 8. So it works. It's just a little different from the even index. So just something to keep in mind. If you're an odd index and you see a negative inside, it does get to come outside. But if you're an even index and you have a negative inside, then we're going to say it's not a real number for now. Okay, so if you look at the first problem, square root of 512, when I first glanced at that, I'm like, I don't think that's a perfect square. So what I want to do to try and break that apart, and again, it's similar to your thinking with these perfect squares over here, like square root of 25. The reason that it ends up being 5 is, well, let's try and factor 25. 5 and 5. So as soon as I see a pair, I know that it's a perfect square. Or if I look at the cube, root of 27, well, that's 9 times 3 and 3 times 3, so I can see my triplet there. That's my perfect cube. So if I'm not sure what perfect square is in there, or if it's even a perfect square by itself, I could try and prime factor it to find out. So I'm going to look at 512 and see what goes in there. So I know that, well, 2 for sure. It's divisible by 2. So 512 divided by 2 will end up being 256. But then 256 can break apart. That's 2 and 128, and then 128 can break apart. That's going to be 2 and 64, and 64, well, that's 8 and 8. I think we're going to end up with a lot of 2's here. So we have 4, 2, 2, 2. So I'm going to circle all these prime numbers. These are all the guys that don't have any legs. They can't break apart any further. And if I were to actually multiply all of these prime numbers together, 2 times 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 2, that would be 512. Now what we're looking for is perfect squares, and I kind of look back a little bit and I'm like, wait a second, I could have stopped right here maybe, because that has a 64, which is a perfect square. But if I keep doing that prime factorization, basically what I'm looking for is pairs, and I could do it with small pairs. So like for this set of 2, I'm going to write a 2. It gets to come out because that's really a 4, and the square root of 4 is just 2. Let's find some more in here. Here's another pair, so that's going to come out as a 2, and these are all going to multiply. Here's another pair, that's going to come out as a 2, and another pair, that's going to come out as a 2. And then we have this little guy still left. He doesn't have a partner, so he has to stay inside. It's not going to be a perfect square, so 2 has to be inside of our radical. So the answer to this, if I multiply 2 times 2 times 2 times 2, that's 2 times 2 is 4, times 2 is 8, times 2 is 16, it's going to be 16 square roots of 2. So that's simplified. Again, it's not a perfect square, but it's simplified. So I'm going to scroll out here just to kind of see how these cards can work. So you can see within the answer, 16 square root of 2, which matched up with my 16 square root of 2. So we're going to try a few more of these. Let's see. This time we have a third root. So in order to come out, we need triplets. We need 3 of something. That way they're perfect cubes. I also noticed that I have a negative inside. So right away I'm going to pull that out because a negative multiplied by itself 3 times makes a negative. You write -1 if you'd like, but I like to leave it just as a negative. And so we're going to break apart 162. Well, I know that's 2 and 81, and then 81 is 9 times 9. We have 3 times 3 and 3 times 3. So I'm going to circle my prime numbers again. So I know 2 times 3 times 3 times 3 times 3 will make 162. Again, since I am in a cube root, I need 3 of something. So I don't have 3 2s, but I do have 3 3s. So for this triplet, I'm going to pull a 3 out. And so I have that 3, and then the 2 and this 3, they don't have any partners, so they're going to stay inside. So we have 2 times 3 inside. And we still have the cube root. So I'm going to write cube root. So please don't forget that. So that way that reminds us that we had 3 or triplets of things in order to come out. So final answer here, this is going to be equal to -3 cube root of 6. And so we're going to check that. Yay! This is the answer to number 2. All right, let's try that again. We have the square root of 24. So we're going to break that down here. Let's see. 2 times 12 is 24, and then 12 is 6 and 2, and 2 is 3 and 2. So then my prime factorization is 2 times 3 times 2 times 2. Now we are in a square root. Remember, if you don't see an index, that's just our regular square root. So we need pairs in order to come out. And so I'm looking, I have a pair of 2s. So for that pair of 2s, it gets to come out. And then for this 2 and this 3, they don't have any partners, so they just get to come out as 2 times 3. And I'm going to keep the square root on there, and I don't have to write that little index of 2, but my final answer here will be equal to 2 square root of 6. Again, let's check our answer. Scrolling out over here, we have 2 square root of 6. All right, let's skip around a little bit more. Let's see, we have some variables going on in here. We have the 4th root, so if we have to do a 4th root, that means we're going to need 4 of something, so little quadruplets, I guess, in order to get them out. And so the 128 is going to be the same exact way as we've been looking at our numbers, prime factor them. That's 2 and 64. 64 is 2 and 32. 2 and 16. I really like 2s. They're the easiest. 2 and 4. Whoa, there's a lot of 2s going on there. So my prime factor is 2, 2, 2. I need, let's see, 5, 6. Okay, 7 of them. So number-wise, in order to come out, we have to have 4 of something. So I'm taking this group of 4. It's going to come out as the 2. And that's all I can do with that. So that means these guys, there are 3 of them, but remember we need 4. So those 3 are going to stay inside. So we have 2 times 2 times 2 inside. And I don't want to forget, this has to be a 4th root. So just dealing with the numbers, we got that down. So now what we want to do is deal with the variable. Now, n to the 8th really means n, 1, 2, 3, 4, 5, 6, 7, 8. And so if we're trying to find the 4th root of that, again, we just need 4. So it's kind of like dividing by 4, if that's a little bit more helpful. So if you have 8 n's and you divide by 4, that means you're going to have 2 sets. And since there's 2 sets, you're going to pull out an n for one of those sets, and then another n for the other set. So our final answer here, this will become 2n to the 2nd power times the 4th root of 2 times 2 times 2, which is 8. So there's my final answer. And we're going to check on that. 2n squared, 4th root of 8. Yay! Okay, I switched over to problem set E. So we're going to look at some of these square roots. They look a little bit harder. A couple more variables anyway, but this process is still the same for all of these. So if I'm looking at this is a square root, so I need pairs in order to come out. I always start prime factoring my number. Now 147, that's not even, so let's try and divide it by 3. If we divide it by 3, we get 49, so that's 3 times 49, and then we have 7 times 7. So these are my prime numbers, my prime factorization. I'm going to be able to take out a pair of 7s. So this is going to be equal to, we get 1 7 for that pair. And then the 3, that guy has to stay inside. So we're going to have the square root of 3. So that's number-wise. But then again, variables, we need to do that. So if it works for you to write out every single value, that's fine, like x, 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 x here. Like x, 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 but that's so many to write. So if I think about it, there are 10 x's and I need groups of 2. So that's going to end up being 5 groups. So we can actually just write x to the 5th. And then z to the 5th, if we think about that, divided by 2, that's going to be 2 groups. So we're going to have z to the 2nd, but that only uses up 4 z's, so that means 1 z is inside. So if you want to see that, I'll write out the z's. 1, 2, 3, 4, and 5. So what I just said is there is 2 pairs of z's. So that's why this has z squared in it. So that's z times z. And then this little z, that's our leftover guy, like the remainder, and he's going to stay inside. So the final answer for this, it's sitting right there, but I'll write it. It's going to be 7x to the 5th z squared times the square root of 3z. And I didn't write an index on there because it is just 2, but if you write a little 2, that's okay. Just be careful with your exponents. So I'm going to zoom out so we can see the answer on here, which is 7x to the 5th z squared square root of 3z. Again, we have the answers on the page following, but it's as if it was printed double-sided, so it's kind of flip-flopped. So if this is the question, then the answer is over there. If this is a question, then we have our answer going on there. Okay, let's try one more here. We have a fraction. That's okay. There's a couple different ways that you could try the fraction. You could try and simplify on the inside if there's anything that can reduce just as a fraction, but nothing here. So then what we want to do is try and break apart each of those. So what I mean is we can rewrite this as the cube root of 8x squared over the cube root of 27y to the 6th. So then you just have two little problems to kind of work on. So I could work on the top first. So I already know 8 is 4 times 2 and then 2 times 2. So I'm just prime factoring. I'm in a cubed root. So as soon as I have 3 of something, it gets to come out. So this will be equal to a 2. Now x squared is only 2x's, so it does not get to come out. So I'm going to have the cube root of x squared still sitting in there. In the denominator, if I break apart the 27, that's 9 times 3 and then 3 times 3. So yay, we have a set of 3 3s. So that's going to come out as a 3. And then y to the 6th, well, that's y. And so how many sets do you see in there? There's 2 sets of 3. So for this set, we get a y. This set, we get a y. So that's going to be 2 y's. And they're outside of that radical. So nothing got left inside on the bottom. So here is the final answer. And let's compare. Looks pretty good. There we go. They match up. All right, so you guys can try the rest, see the answers on there, and if you have more questions, we'll talk about them during our Zoom. Try and do at least 20 of them, and you can record your answers and problems on page 77 of your book.